Good day, everybody. So let's take a look at the topics for today's review of certain organic chemistry intro topics. So this time we're going to concentrate on the following. So this is going to be about organic acids, carboxylic acids, chiefly, amines to some extent, and alcohols and aldehydes reactions, right? So what we're going to do is take a look at the kind of advanced topics related to the reactions between aldehydes or ketones and alcohols, right? So previously, we were talking about how you can react one molecule of aldehyde with one molecule of alcohol, right? So by the sound of those terms, you should be able to translate the words, right, into the chemical reactions, right? So draw some sort of aldehyde and the alcohol molecule, right? So, but now we're going to do that on the whiteboard, right? So it's going to be item 1, for example, here. So we are going to take a look at the formation of aldehydes, right? Not aldehydes, but hemiacetals from aldehydes, and then the full acetals from hemiacetals, right? So that's going to be our sequence. Okay, so let's take a look at some sort of aldehyde. Maybe we're going to use the aromatic aldehydes, such as benzaldehyde. That's another actually generic name or common name of an aldehyde with an aromatic ring, right? So that's what you kind of like do if you want to show the structure of benzaldehyde. So let's imagine it's going to react with one molecule of alcohol, right? To form, according to our general knowledge and the generic reaction, right? So it's going to form the hemiacetal in this case. So we're going to work maybe with ethanol, let's say ethanol, or maybe let's do one propanol, for example, right? So one propanol will be like this. So 3 carbons and OH, right? On carbon number one propanol. Okay, I'm going to show the uh, reaction conditions. Okay, so then we're going to form our final product at this stage, right? So it's going to be step A, let's call it, or maybe step 1, whatever, right? So that's all good. So we're going to form, as we know, the OH bond and the CO bond, right? So these are two new bonds which will be formed. So apparently the OH bond will be broken, right? And then this one carbon-oxygen bond will be broken, the pi bond will be broken, right? So now let's show what we are going to obtain as a result. So we are going to, okay, leave only one bond left over, right, between carbon and oxygen. Okay, very good. So now this bond is going to be broken, and then we're going to make OH bond instead. Okay, 1. So CH bond, this CH bond stays, right? So now you're going to make the carbon-oxygen bond. So just draw that carbon to oxygen, and then this oxygen doesn't have H anymore, right? Because this H is now here, right? So this guy is here now. So now, however, this oxygen has left over 1, 2, 3. So 3 carbon chain here. 1, 2, 3. Okay, good. So that's your hemiacetal. So part B will be take this hemiacetal and react it with the second molecule of alcohol, right? So as you see, total we can react, right, up to 2 molecules of alcohol with 1 molecule of aldehyde. So we are going to continue with the hemiacetal, and then we're going to use just the same alcohol, right? It's entirely possible. So that's our hemiacetal. I'm just trying to do a good job redrawing that without losing any atoms. So, which is what happens sometimes. Okay, so then I'm going to add the alcohol, same alcohol, right? So just second molecule of the same alcohol. So that's my 1 propanol. So I'm going to use acidic conditions, right? So H plus stands for the acid, right? So it's going to be acid source of some sort, right? So an H plus is a kind of like general sign that you are going to conduct this reaction in acidic environment of some sort, right? So, and then the procedure typically, like for a particular synthesis, will specify what kind of acid you are going to use, right? Maybe it's going to be HCl, maybe it's going to be some kind of like weaker acid such as HF, right? So it depends on the chemical reaction, indeed. So now, what's going to happen? So generally speaking, right? So you are going to eliminate OH from your hemiacetal, and you are going to eliminate H from your alcohol, right? During the formation of full acetal, right? So as a result, you are going to eliminate water, HOH. So like H2O will be released. So you can just say minus H2O. That's kind of an exception when we can use minus with actual chemicals, right? So, but it's not kind of like the main product, right? So that's why we can show it even under the arrows, right? So we're mostly concerned in organic chemistry with the formation of the organic product, right? So redraw some things. So this will stay. Okay, good. So now we're going to switch this OH to, guess what, carbon-oxygen bonds. So you see, here we have free electron now, right? So to make the covalent bond. And on this oxygen, we also now, upon the loss of the H with the electron, right? So we just now assume that we're just going to straight up homolytically break the OH bond, right? And then H will get away with its electron and oxygen will get away with its electron from the bond breaking. So now those two black dots signifying two electrons can be connected to make a covalent bond. I'm going to just redraw them. All I need to do is move them closer in space, right? So it's not even a chemistry skill. Maybe it is, who knows? So, and now that this is done, this is complete. This is going to be your acetal, right? I'm just going to say like what it is, right? Hopefully you'll be able to distinguish. So that's your hemiacetal, a known term. That's your acetal. Okay, great. So now you can do the same with ketones, right? So the only difference is that you are going to track something I'm going to show in the red color. So the only difference will be basically, so in the ketone, like basically any reaction of ketone, right, you are going to have not an H instead, right, but some sort of alkyl chain typically. So like maybe it's going to be instead of H here, right, in red, you can, for example, have methyl. Maybe it's going to be ethyl, pentyl, isopropyl, right? So like you name it, you can literally do it like with your practice and track and then make sure that this doesn't go anywhere when you do the first of all hemiketal formation. If this is not an H but some sort of alkyl chain, for example, then we'll start with a ketone, we'll make a hemiketal, right? So and now here you are going to have not an H again in your hemiketal, but it's going to be maybe, let's say, propyl, right? Or isopropyl, let's say, isopropyl. Maybe it's going to be phenyl, whatever, something kind of like with a carbon chain, right? So then you have the ketone here, right? So basically, or rather hemiketal at this point, so which will be reacting in the same fashion, right? Except this will be kind of like not an H, but it will be some sort of alkyl chain. Let's imagine for the simplicity ethyl, 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 ethyl. It literally doesn't change. It stays the same. It stays the same. Don't touch it, and then you'll be out of trouble. So yeah, pretty easy. I don't like want to even like explain it, so because it's going to be better for your practice to kind of like review it yourself, right? With me just prompting you to do that. So okay, great. So now that was items 1 and 2. Basically, now let's take a look at the carboxylic acids and esters, kind of in the blended format, right? Just a disclaimer, we cannot highlight every single question on the exam, right? So the point is just to be holistic and for you to kind of like recognize some kind of like weak points, right? It's like you'll be like, oh my, so maybe I need to review something kind of like what's an aldehyde or what's an alcohol, right? So I cannot predict what's in your head, right? So what kind of problems you're going to encounter like as you watch the review. So a lot of that is your own work, and then for me it is just kind of the optional thing actually to provide reviews. So just kind of keep that in mind. and apply your effort, right, as well. So that's going to be amazing. So now we're going to item number like 2, basically, right? So let's take a look at carboxylic acids, right? So generally, so by the way, I'm not going to say what it is, so you're supposed to know what it is. So that's your carboxylic acid. I'm going to show this bond specifically, right? Why, right? So maybe you can answer this question, right? So because it's going to be needed for the dissociation, the famous dissociation of the acids, which is going to be our basically like first chemical reaction, which we're going to look at, right? So when we look at esters, right? So they are known as derivatives of carboxylic acids, and they look something like that, right? So these are your acids, these are your esters, right? So and then R could be here, for example, ethyl, let's say, right? So R, that's R prime. R can be, for example, alkyl chain of some sort, let's say pentyl, right? Maybe it's isopropyl, maybe it's phenyl group. So, and then you can already like imagine that you could have like a myriad of various structures of carboxylic acids, right? And esters, like in nature, in the synthetic organic chemistry, medicals, medicine field, and so on, right? So now let's take a look at the reactions. Item 3. So first of all, acids, right? So acids, what are acids? So acids are compounds that donate an H plus, donate a proton, in other words, right? So I'm going to show this bond. It's going to be like this kind of like thick bond, which will be participating in the dissociation of the acid, right? So that's going to be happening with like any carboxylic acid, by the way. Don't touch anything else upon dissociation. You've been warned, right? So multiple times. And then if you do that on the exam, well, um, we'll deal with this on a case-by-case basis, right? So then you have, oh, sorry. So you have some sort of dissociation, right? So maybe it's going to be in the aqueous environment, typically. And then you are going to have the following, right? So like for now, we're going to show it without actually the presence of water. So then we just need to simply show the two ions which will be formed, right? As I told previously to myself, don't touch anything else except this bond. So, um, okay, so we're going to form the H plus. So this guy, this hydrogen atom, right, now turns into the H plus by losing the electron, right? So now you have H plus. So basically what happens is that in the course of dissociation of any carboxylic acid, this pair of electrons, 1, 2, moves to the oxygen. Boom. So now oxygen, that's the oxygen electron on the left side of this squiggly line. This is the electron from the hydrogen, right, on the right side of the squiggly line. This entire pair moves towards oxygen, or in other words, this electron moves or gets added to oxygen and it's lost by hydrogen, this electron. So hydrogen becomes H plus because of the loss of electron. It used to be the hydrogen atom with a charge of 0. Now it lost one negative charge, became H plus, right? So just charge balance. So oxygen also used to be a neutral atom, but now it gained an extra electron. Consequently, we must put the minus sign on the oxygen. 0 and minus 1 becomes minus 1. 0 minus minus 1, when we talk about the H, right, losing its electron becomes plus 1. 0 minus minus 1, minus 1 for the negative charge of 1 electron, then you have to make H plus as a result. So show the original lone pairs. Sorry, this is the lone pair, lone pair. So they prevail, they stay, right? And now you're also going to have this like big pair of electrons, or the pair of big electrons. Let's show it this way, right? So that's it. No electrons on this one, right? So proton is literally devoid of electrons by its definition. So here we go. This is the acid dissociation. We can show it with water. So that's kind of going to be like a general chemistry skill, to be honest. So, but let's use some kind of like acid like this. Plus H2O or HOH. I can write it this way. It's a weak acid reaction, right? So weak acid ionization is a reversible process. So we're going to show our counter ions. So I'm going to redraw carbon chain. 1, 2, 3, 4. So the electrons moved. Now you're going to have your negative charge, right? So, good. What happens next is that this is going to be your acid. This water is kind of like amphiprotic, right? It can act as an acid or as a base. So if the carboxylic acid is an acid, it's literally in the name, right? So it must act as an acid. So that's what we can like, imagine for now. So then consequently, that has to be the base. You cannot have acid-acid reactions. We never talked about that, right? So then acid, base. So that we talked about. So consequently, water will act as a base in this specific reaction, right? So it will accept the H plus, right? That's what bases do. It will accept the H plus from the acid, right? As a result, it's going to form the hydronium ion. So these are the original H's on the water. And now you recall there is a lone pair, right? Lone pair will act now as something that can be turned into the covalent bond. So basically, let's spread out this lone pair, big electrons. Let's make it like that, right? So coincidentally, we have this hydrogen, right, which will be gained by the base. Put it next to that base, right? So now, as you see, it's not the hydrogen, it's a proton, right? Proton technically is gained, like more specifically, more correctly speaking. So now also what happens is that this lone pair is shared. So one electron, one big electron is gained by the H plus, right? So, and now H plus becomes like this, H plus and minus one and one electron plus negative charge, one negative charge becomes original H plus and minus one becomes zero, right? So basically you make this H with a dot turns into the H atom, right? So just go from H plus somewhere on the way to H with a dot. And now it's going to be positively charged, neutrally charged atom of hydrogen, H with a dot, right? So what happens to the oxygen? Oxygen lost one of those electrons, right? Oxygen used to be neutrally charged, but now it lost one of the electrons. Now this big electron is here. It's not on oxygen anymore. It's with the former H plus, right? Which now became an H atom. So consequently, if oxygen loses one negative charge, it has to develop a positive charge. Put the plus on oxygen. Now connect the two electrons, and now you made your hydronium ion. That's it. So that's your like acid-base reaction. And specifically, we can also like call it a proton transfer, right? So like in other words, so it's a proton transfer because a proton is transferred from the acid, being the carboxylic acid, to the water being the base, right? As a result, you are going to form your conjugate base. It's a general chemistry term, conjugate base. So this is an acid. So, and then you see there is like opposition going on, right? So you start with an acid and you form the opposite. So when you are on the right side with the word conjugate as well, right? So it's kind of like connected, right? So acid makes the conjugate base from itself, right? Conjugate base, acid, conjugate base, right? So now, by the same token, if this is a base, it has to form this. What's that? So that's conjugate acid, right? So just like the same token, the same like reasoning behind like assigning the terms to those compounds. Correspondence, acid, conjugate base, kind of opposite and conjugate because the conjugate stuff is formed on the product side, basically, right? So then base here forms the opposite, acid. Conjugate acid because it's formed on the product side. Okay, good. So now let's take a look at the reactions. It's going to be item 5. Acid-base reactions. So maybe let's take a look at some generic acid. What if I want to react it with an inorganic base, such as KOH? Well, we can do it. So KOH is an ionic compound, K plus OH minus. I'll put it in parentheses to avoid confusion. Okay, it is OH. The entire OH thing is negatively charged. Not H, not O. The entire thing is negatively charged. Upon dissociation of the acid, we are going to form the ion, which is going to be like this big thing with a negative charge on this oxygen specifically. And also, of course, will form the H plus, right? So So then we're going to show the reaction product. Ion exchange has to happen. I'm exchanging the old positively charged ion to the new one. This is negatively charged, OH minus doesn't work. So K plus is your best option. Done. So now, same thing here. So let's connect the leftover things. OH minus and H plus, and great connections. So they make nothing more than water. Done. So, acid-base reaction. Next, moving on. Oof, sorry. So 6. What do we do here? Let's take a look at esters, right? So esters are derivatives of organic acids. They're formed like that. Via what? So we learned one way. It is basically, or like the first way that we learned was the Fischer esterification. So Fischer esterification. I'm just saying that. So that's your acid. Has to react with what? Some sort of alcohol. So now it's the power of your imagination. Imagine the R is pencil. I'm not going to draw it in the interest of time. Imagine that now. So you need to be able to draw that, right? So that's why I'm kind of like aggressively prompting you to do your own work. So it's for your benefit. So this one is R. Let's say R prime is pencil. Recall it. R double prime is, for example, phenyl. Recall it. Okay, great. So now I'm going to show them actually in the product. So we will have here Fischer esterification in the presence of H2SO4. Okay, so what's going to happen is that the pattern, which is applied to like any combination of acid and alcohol, will be like this. So turns out, experimentally, it was determined that the acid has to lose OH, right? So I'm just saying that, but don't confuse it with the acid definition. It's just how this particular reaction works. It has nothing to do with the acidity, right? At this point. So the alcohol has to lose H, right? So those things will be eliminated. So now you're going to connect free electron, free electron. Let's say this is pentyl. Okay, I can show pentyl. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's your pentyl, 5 carbons. Carbon. So this is phenyl. Our double prime is phenyl. Okay, O survives with its electron. Phenyl, not a problem. I can show the phenyl. So let's just draw this here confidently. So, and then this is your ester. And this is your ester. You made it. Congratulations. So, you can name it, right? So that's going to be phenyl, 1, 2, 3, 4, 5, 6, hexanoate. So you have the hexanoic acid, right? And then you have phenol as your alcohol. Then when you name them, you are going to start with the name of this guy. So just, what's this group? It's phenyl, right? Maybe it could be methyl, right? Depending on the nature of R prime. So maybe it's ethyl, isopropyl. I don't know. So it could be, it's dependent on the case, right? So phenyl, and then what came from the acid? What kind of acid was it? 1, 2, 3, 4, 5, 6. Hexanoic acid, it used to be, right? So this used to be the hexanoic acid. So like with an H, of course, right? So then you are going to form the ester, which will be named as phenyl. And then hexanoic acid will turn to hexanoate, right? So to make the ester name. So phenyl hexanoate. So 2 words. All right. So that's your ester formation. So now let's take a look at other ways to form esters. So previously we were talking about the so-called acid chlorides, which can be, so that's item 7, which need to be, first of all, synthesized, right? So how does it work? So we start typically with some sort of acid, and now we're going to add to that SOCl2, right? So this is going to be our first reaction, which will eventually lead to an esters via the chain of reactions, right? So And then at this point, we're going to make our acid chloride. It's going to be the compound, which is looking like that. So this guy becomes switched to Cl, right? So because we make the acid chloride, maybe it could be acid bromide. So if you have Br here instead of Cl, then you'll have Br here instead of Cl, right? So just kind of like be aware. So they are called, technically, this is a class of compounds, not just only acid chlorides that exist, right? So there could be like acid halides, and halide stands for a halogen atom, right? So, but typically people use acid chlorides because they're like easily accessible. So since this compound is easily accessible, but you might as well have access to some sort of like bromine carrier that will attach the Br atom here instead of chlorine atom. So acid chloride. So step number two, let's make the ester from the acid chloride. So that's going to be an alternative pathway to esters. So how do we do that? We still reacted with an alcohol, right? So let's show the alcohol. I'm going to explicitly show this bond, which will be broken. And this bond will be broken, right? So Cl and H will be eliminated. Here we have some alcohol. So maybe like, yeah, whatever. Let's imagine that our double prime stands for hexyl. That's for your practice, right? So draw the hexyl. So this guy could be phenyl. So draw phenyl. So I'm going to draw the final product, which is going to be looking like this. So we'll have R, phenyl, gun, and gun. So then we have the carbon, oxygen. You see, you need to make an ester. Don't randomly attach oxygen here, right? So, or here, somewhere to this R, right? So it's not going to work, right? So this is your attachment. So it's free, right? So it's as if, imagine you need to go through some kind of like exit, right? So just go through the door, which says exit, and it's open, right? So don't go through the window, for example, right? So which is closed, or some kind of closed doors. So like, don't do that. It's just, I don't know, some sort of chaotic behavior, which is not applicable here, right? So maybe somewhere else you can be like chaotic and adventurous, right? So there is a time and place for that. So, but at this point, we just need to be okay, well, dot to dot, right? Discipline and such. So it's a good skill to have at the end of the day, even if it seems boring, but apparently it's a good idea to be bored sometimes. So, and go through tedium. It's also good. So this is our ester that we formed from the acid chloride. So now we're moving on to the next topic, which is going to be hydrolysis reactions. Item 8. Hydrolysis wise, we can think about the following, right? So that's basically the reverse of the ester formation. So then we need to start with an ester as our reactant, right? That's going to be some sort of ester, which is going to be looking like this, right? So this is R prime, just different groups, right? Maybe this is ethyl, this is, for example, propyl, right? So just use your imagination at this point. So you're going to add water. So some people were blasting me for not showing the water. So, but yeah, it's a legitimate claim. So, and then you are going to use the H plus, right, as your additive, your catalyst on this reaction. So as a result, what's going to happen is the following, right? So you're going to, turns out, break this bond, right? Then you are going to form your alcohol. So this stuff in circle, like R prime O, almost looks like an alcohol, except you need to add H to that, right? So now this stuff in this kind of like cloudy circle, right? Almost looks like acid without OH, right? So necessary for the carboxylic acid. So let's add this. And now we have cloudy becomes your acid, right? So let's show that this way. Acid with the acidic hydrolysis. Okay, so that's number one. Number two, you have your alcohol, right? So also electron, electron, H with an electron, and then O with an electron. Okay, so uh, That's it. So that's your acid and alcohol that are formed, right? So and then if you react them again via Fischer esterification, you will make an ester again, right? So that reaction is going back and forth, right? It's a reversible process. So yeah, so that's what we have, right? So then that's going to be our acid-assisted hydrolysis. And now we have like the ultimate item. Here is going to be our item 9, perhaps, right? That is the so-called base hydrolysis. So what happens? We're going to start with an ester again. Sorry, ester. So now we're going to get a base, such as KOH. Reaction arrow continues here down the line. And then we're going to make the following, right? So here's a little bit different split. Two straight circles will connect to make the salt of the carboxylic acid. Two cloudy circles will connect to make the alcohol. Let's start with an alcohol, doesn't matter. Electron, electron. Then you make the bond. So that's your alcohol, done. So now moving on to the salt, right? R prime, C double bond O. That's a double bond right here. Electron, right? This bond is broken. And then, yeah, there is also technically kind of the electron that will show up eventually, right? So, and we have to have it anyway. So as we know, so there is an electron, right, as well on the oxygen. Make the bond. Don't forget the K. If you have this formation, right, so then it's a sign that you are going to have the charges, right? So because we know the salts are ionic compounds, and then these are those ions, right? So K plus ion, and then this like negative charge. Technically, this is the entire ion, right? So that's your ion, anion, specifically derived from the carboxylic acid, right? So this is your K plus ion derived from the like inorganic base KOH. And that's it, right? Now you have your potassium carboxylate, right, of some sort. So like maybe let's say R is like 4 carbons. That's the fifth carbon, right? So 4 carbons, like just butyl, right? So with this, you'll have 5 carbons total. So it's going to be pentanoic acid, and then you have the salt, the potassium salt of pentanoic acid. It will be known as potassium pentanoate, almost like an ester name. Okay, great. So, and yeah, that's it. That's your stuff, right? So now you can like practice like, I don't know, like generate 10 or 5, 10 reactions, right? With whatever R prime and R double prime groups you want, right? So, and whatever also is not very broad, right? So at our like level, it's going to be basically some kind of alkyl chain. So which will again prompt you to like name or recall the names of like what's a hexyl, pentyl, right? And so on. Phenyl, so like use those, like you can use aromatic things, right? So maybe with some substitution in the ring as well, so you don't have to like name them, right? So you need to be able to draw them, like first of all, right? And draw them in various fashions, such as like skeletal drawing, condensed structure, right? Line angle structure, expanded, and so on, right? So there are many like skills to exercise before you need to like worry about naming stuff. So naming is still kind of like a legitimate like, question, right? So, but it's like pretty fundamental as well for us. You don't have to like name some kind of like crazy natural product molecules, for example. So, yeah, now item 10, our like ultimate item. So it's going to be about amines, right? So we just like talked very briefly lately about amines, and then we're going to develop this topic in the future, considering we still have some like study time, so to speak, right? So amines, so like what can we imagine about them, right? So they are essentially derivatives of NH3, right, which is ammonia. So and then what happens is that you can just from our perspective or break the bond, make the bond, right? So we don't care about like the actual like formal performance of this reaction, right? So we're going to break this bond, right, somehow. And let's imagine that somewhere we have the CH, let's say ethyl available to us, right? So we'll jump into the deeper end a little bit. So that's an ethyl. Ethyl has to have the opening, right, for the to make the covalent bond, for example, right? So it has this one electron. And now imagine that this is eliminated, right, somehow. And then also ethyl is generated somewhere else, right? So, but now you see there is a free electron, available electron on nitrogen and ethyl. They can connect and make the bond. And then as a result, you are going to make your amine, right? So that's your first amine. Maybe not the first one, right? So nevertheless, so that's the one, right? So amines, this is an example of the amine. So they're called typically. So this one is called kind of easily, right? So just put together the two things, right? Ethyl amine, and that's it, right? So, or you can call it amine for now. So like, because we didn't get to the nomenclature yet, right? So just call it like amine one, right? So amine two, whatever, right? So like P1, product one. So yeah, and then amines, so we can just take a look at their like basic properties. Their bases. Let's take a look at our example amine just from just now. That's what we're gonna have, right? So they are bases, right? So how do they, what does it mean? So bases accept the proton, right? So we are going to show the proton. So maybe the proton will be donated by an acid, right? Such as water. Let's do that. Quite exciting. So we continue our like arrows down the page here. So they accept protons, right? So first of all, you can start with the breaking of this bond, and then if water loses H plus, it will have to generate OH minus. Let's just leave OH minus right away. And now we are done with that, right? So we have the, basically, if this is the base, amine is the base, right? So this is the water acts as an acid, right? Water is amphoteric. So acid forms the conjugate base. So we can assign the terms to that. Good, right? Conjugate base is formed. So now, next, we are going to go from the base to the conjugate acid. We are going to make the acid out of that, right? So now base accepts the H plus. So let's see. They have to make the bond, right? So that's what it means by acceptance, all right? Like the further like development of the acceptance will be making of the bonds. So we have our previous bonds. Okay, they survive, right? So then you see there is this lone pair of electrons, which again need to give you some understanding of what's going to happen next, right? So the pair of electrons is two electrons. Two electrons can be also used to make a covalent bond. So spread out, and then you will make the covalent bond. With what? With the incoming H proton, right? So H used to be like no electron, but now, if we do that, we'll show that this proton, right, proton, gained an electron and turned into the H atom, hydrogen atom, with a zero neutral charge, right? So because H plus accepts one negative charge of like one electron, and it's going to be plus one charge and minus one charge from the electron becomes zero, right? So then you make the, as a result of this, as well, you make the hydrogen atom, right? So, and then charges kind of like, yeah, generate themselves along the lines. So then what happens next is that we are going to form the bond, right? So you have H with the dot, N with the dot, and now you are going to make your bond, right? So the bond will be like this. So it's going to be the new NH bond will be formed, right? So that's your incoming H, right? So used to be like H plus somewhere along the lines of the reaction, now turned into the H hydrogen atom, right? So nitrogen used to have count, that's the outer shell, right? 5 electrons. Now it has only 1, 2, 3, 4. It lost one electron towards the H plus, right? To turn H plus into H with a dot or H atom. So now it has only 4 electrons, nitrogen, right? Nitrogen does. So what does it mean? So it used to have the charge of 0, the nitrogen atom. Now it lost one electron, consequently it has to generate the positive charge to counterbalance, right? So neutral thing lost one negative charge, generates on itself one positive charge, right? So just like maybe you lose something negative, some kind of like negative emotion, then you will generate potentially a positive emotion, right? So like maybe this not happen, a little bit more complicated in the human nature. So, but in terms of the nitrogen nature, so it's more straightforward, right? So, and here we go. So that's our base makes a conjugate, right? As we know from our previous knowledge, conjugate acid, right? If you look at this compound, so it really can donate H plus. It cannot accept H plus because it already has a positive charge. They'll repel one another, right? So it will more likely to donate, lose H plus than accept it, right? So if we choose from two options. All right, so at this point, we are done. So thank you for your time and attention, and stay focused. Bye, everyone.